Well, today we put into practice what we've learned about superposition over the last couple of lectures. And so what we're going to be doing is covering the two final topics of the course, which is going to be interference and interferometry, and then that's going to be followed by diffraction. And in both of those topics, superposition and interference is playing a central role. So we're going to start this new topic of interference and interferometers by looking at Young's double-slit experiment. And so this is actually a very simple experiment. It was one of the very first experiments ever done that explicitly used or demonstrated interference. And it was done by Thomas Young in 1804. And that was back when most scientists at that time still thought that light was made up of massive particles, and there was a small group of dissidents who believed that light was composed of waves. And so Young's double-slit experiment was one of the first definitive experiments that showed that light was in fact composed of waves, although, as we all know now with the photon, it's also particles, so there's the wave-particle duality. Anyway, so with Young's double-slit, what we have is a plane wave which is incident on a double slit in an opaque mask. And so we've got this plane wave coming in, and so there's just going to be this k vector for this plane wave, and it's going to diffract off of each slit, but we're going to be doing diffraction in the next set of topics. And so what we're going to do here is just assume that these slits are very small. And so each slit, and these are like vertical slits, and we're looking at them in cross section. So if you're looking down from the top, what happens is that each slit is acting like a point source, and so that essentially the waves will spread out in these. Now they're going to be actually cylindrical waves because these are long slits, but these will be spreading out. And so then there's going to be an observation screen somewhere off to the right, and it's actually going to be a fairly long distance to the right. And so this is where we actually start to have to put length scales on these things. So let's say that this is some distance L away. Now we also have a characteristic length, which is the wavelength, right? So there's going to be a wavelength for these spherical waves that are coming out, and then we've also got the separation between the slits, and we'll call that B. And so we've actually got three length scales. We've got B, we've got lambda, and we've got the distance to some distant screen where we're going to be seeing interference effects as these two waves overlap. So generally when we're dealing with interferometry, we're in a situation where we're both B is, well, first of all, B is going to be on the order of lambda, although typically it'll be bigger than, but of the same sort of comparable size. And what I mean by comparable is going to actually be a pretty broad range. And so we know that the wavelength of light is about 1 micron. Now, green, which is in the center of the spectrum, is actually half a micron, but I just sort of, for rule of thumb, when we're just talking length scales, I'll very often just say that light's 1 micron, whereas technically that's going to be in the near infrared. But anyway, so if the wavelength of light is a half or 1 micron, the slit separations will typically be in the range of, let's say, hundreds of microns, right? And so they're not equal or even, necessarily comparable, but still, 100 microns is maybe just 100 wavelengths, let's say. Whereas this length L, which is the distance to the screen, this is taken to be much, much greater than both B and the wavelength. And so the distance to the screen is often considered to be at infinity, and we'll say that the screen is at infinity. And so the difference of being at infinity or at some finite distance often isn't a large effect, and so we'll very often just kind of assume that the screen is off sufficiently far that it's essentially like the rays coming from these slits are going to be going off to infinity. So the reason why I'm bringing all this up is because we do have to do geometry on this. And so the way that this looks is I'm going to replace the slits with just 2 point sources. And so there's a distance B between these point sources. And then I'm going to look at rays that are heading off to some distant screen. And so I'm going to have these actually going off at equal angles. And that's kind of the point, because if the screen's far enough away, rays that are leaving at equal angle are going to end up at the same point on the screen off at infinity. And so these are both angled at theta. And so this is an angle theta, and this is an angle theta. And so then I'm going to drop a perpendicular from the one ray to the other. All right, so that's perpendicular. And so what that means is that when they arrive at infinity, or at the screen, there's a path difference given by this thing down here. And that path difference, just with a little bit of geometry, is b sine theta. Okay, and so if I'm looking at some angle relative to the optic axis, and so there's going to be an optic axis right down. So that optic axis is going to extend out to the detection screen. And I'm going to be looking at some angle relative to that. And so what's going to happen is, as I change my angle, there's going to be a changing path difference. And so then this is where optical path length comes in, so OPL. So optical path length is the way we think about path differences when we're working with interferometers. And so we know that if the optical path length difference is a full wavelength, then the two rays, or the waves that are associated with the two rays, will be in phase. Whereas if the optical path length is a half wavelength difference, then there's going to be a difference of, and then we're going to have, they're going to be anti-phase, which means that there's going to be destructive interference. And when they're in phase, there's constructive interference. So what's going to happen is, on a distant screen, as we sweep off of the optic axis, what we're going to be picking up, and I'll just draw this, we're going to be looking at an intensity on the distant screen, and we'll be, let's just go as a function of y. And so what we're going to see there is an intensity. I'm going to have a maximum intensity right at the center of the screen, and then it's going to go down to 0, and it's come back up to a maximum, down to 0. And so this is what we're going to see as we change our detection position y on the distant screen. Okay, and so what we want to do is come up with an equation for this interference pattern. Now, we've already several times in this course seen what happens when we have two waves that are added together, and we know that we get the classic cosine squared. And so that's actually what we're going to get again, but we're going to relate it back directly to the slit spacing b. This position y will also be related then to the distance to the screen and to the angle. Okay, so let's actually start to put that all together. So the equations for this are that I'm going to have an electric field. So let's go ahead and think of this in terms of light. So I'm going to have an electric field coming from slit 1, and then we're interested in looking at that as a function of position and time. And so that's going to be equal to E01, and then I'm going to have e to the I, and then it's going to be, and I have to do a K1 dot R minus omega t. The reason I have to do a K1, and let me just go ahead and do E2, that's going to be RT is equal to E02, and then e to the I K2 dot R minus omega t. The reason why I'm doing K1 and K2 is because if we think in terms of a screen that's a finite distance away, all right, so let me just kind of draw that. So let's say here's my screen, and I have an observation point. Observation points are usually denoted with a capital P, and so let me actually draw the paths. And so at a finite distance away, I actually have two k vectors. I've got a k1 and I've got a k2, and you can see that they are tilted slightly differently. And now this is actually different from when we assumed that the screen was infinitely far away, because in this case these angles are the same. Right? So we look at these angles here, that was theta and this was theta. And so by putting the screen off at infinity, we don't have to worry about actually the fact that K1 and K2 are in fact different. So that even though K1 has the same magnitude as K2, right? So K1 magnitude is the same as K2 magnitude, which is just 2 pi over lambda. But K is a vector, and so if they're pointing in slightly different directions, then in fact they are distinct vectors. And that's why I'm keeping, in this case, the K1.r and the K2.r. When the screen goes off to infinity, then those end up asymptotically becoming the same, and so then the distinction maybe doesn't seem like it matters. But there are lots of interferometric configurations that are not detected off at infinity. And so it's actually good to keep in mind that K vectors are actually vectors, and even if their magnitudes are set by lambda, they can point in different directions, and that makes them different vectors. Okay. All right, so what we're going to do is take these two waves and just add them together, and then take the modulus squared, because that's what an intensity is the modulus squared. All right, so continuing that, what I'm going to get is that the intensity at the observation point P is going to be equal to, or go as, and this is where I'm going to start using, again, shorthand notation. So this is going to go as, the E total, which is the sum of those two, and this is a complex valued object, and then times the total E field complex conjugate, okay? And so then that's going as the modulus of ET squared. Now again, there's coefficients out front. There's going to be a 1/2, there's going to be an epsilon, epsilon naught, and there's going to be speed of light, and that's what gives us the flux. Would give us the Poynting vector, and then the time measure of the Poynting vector is the detected intensity I. But for most of the rest of what we do here, we're not trying to do calibrated luminosity, and so we're just going to take the shorthand that intensity is going to just go as E field squareds. Okay, we're not going to worry about the coefficients out front. Okay, so when we do that, then what I'm going to get is that IP is comparable to E1 plus E2. I am going to go ahead and make those vectors. So this will be a dot product. It'll be E1 plus E2, and then complex conjugate. And so when I do that, and we've done this before in this course, we know that what we're going to pick up is a E1 squared plus an E2 squared plus, I'm going to get an E1 dotted into E2 complex conjugate, and then plus E1 complex conjugate dotted into E2. And these are all actual dot products, all right? So these are dot products here. And so if the E1 and E2, if they happen to be orthogonal, we actually won't get interference effects. And so orthogonal polarizations of light will not give interference. So the reason why we get these interference effects is because they're going to be copolarized, right? E1 and E2 are going to be copolarized. And in the double-slit experiment, that's a natural consequence, because even if the light source, if the light source, the incident plane wave, if it's polarized, then the two spherical waves will actually share the same polarization, and so the E1 and the E2 will actually, those vectors will be pointing in the same direction, and so we'll get a unity dot product, or what am I trying to say? They're coparallel, and so we get a maximum dot product on them. All right, and so that's what's going to give us the interference. All right, so let's look at E1 and then dotted into E2 complex conjugate. And so that's going to be the amplitudes E01 and then dotted into E02. And I won't put a complex conjugate on that because those are, well, actually I guess I can, because these can be polarizations, and we do know that left and right circular polarization have complex expressions. And so let me go ahead and actually put a complex conjugate even on that amplitude, because that's going to include polarization effects. And then I'm going to get an E, and it's going to be I, and then K1 vector minus K2 vector, and then dotted into R. And I'm also going to drop the time dependence, because we know that in the end, if we just are looking at intensities, we're going to be getting cosine squares of omega t, and then the average of that just gives me that 1/2. And actually that 1/2 is where that 1/2 is coming from. Okay, so I'm going to drop that time dependence so that what we're doing is just looking at the spatial effects of interference in this case, in this double slit. All right. So k1 minus k2 is actually another vector, right? So k1 minus k2 is actually some vector capital K, all right? And the magnitude of capital K is going to be 2 pi over a periodicity. And so that's going to be the fringe spacing. And so when we do the interference experiment, we're going to get parallel sets of bright and dark fringes on the screen, and the periodicity length of those fringes on the screen is going to be this capital lambda. Okay, so then what I'm going to get is that the interference effect, and I'm just going to call that I12, the interference effect will actually be twice the magnitude of E01 divided into E02 complex conjugate. And then there's going to be a cosine of capital K dotted into R. Okay? So let me then just write the final intensity. The intensity that we're going to be seeing on the screen at observation point P is going as I1 plus I2 plus 2. It'll be the square root of I1, I2, and then cosine of this capital K dotted into R. All right. And then we've seen before that we like to actually draw this as a total intensity that has a modulation to it. And so that's 1 plus M, and then cosine. And I'm going to go ahead and introduce delta, which is the phase shift. And that's really what's changing as we move up the screen, as we go across the bright and dark fringes. We're changing the total optical path length difference between the two slits, and that's going to be showing up as a phase that increases as a function of y. And then we saw in previous chapters that m was equal to twice the square root of I2 over I1 plus I2. And so what we finally want to get at is this phase delta. Okay, and so we have to see what that phase delta is as a function of the geometry of our experiment. Okay, so for this purpose, let me go back to a finite distance to the screen, and it's really just to, I think, just kind of help illustrate the fact that we are making approximations. And so I'm going to have an observation point off here. So here's my observation point, which means that I'm going to have these rays are going to be tilted at slightly different angles. So there's going to be one ray, there's the other ray. So this will be R2, which is a vector, and this is R1 vector. And even though I've drawn them, close by, I am going to go ahead and actually drop a perpendicular to this, because if the distance is far enough away to the screen, then these rays become asymptotically parallel. I'm just going to shift notation. I'm going to call this A, is the separation between the slits. And let me also actually just kind of name some of these points. All right, so we've got point B. I'm going to call this point B, and I'm going to call this, slit 1, slit 2. So the distance S1b, so the geometric distance S1b, is actually given by the difference between R2 minus R1, and I'll take an absolute value on that, and this is going to be approximately A sine theta. All right, And so that's making this approximation that the screen is very far away, and so R1 and R2 become parallel. So let me then denote this angle here. And so let me denote this angle as being theta. And so it's clear that the distance y, so as I go up the screen off the optic axis, I'm going to have that y over s. Oh, I guess I need to give this, well, actually, it's going to, let me call that L. In my notes I have it as S, but let me just try to be consistent. So the distance to the screen is L, and so y over L is tan theta. And almost, well, I don't want to say almost, I mean, often we'll make a small angle approximation. Actually, there are times when we won't, and so don't just assume that we'll always be making the small angle approximation, but often we'll just say that tan theta is approximately theta. And so then what that means is that this distance, S1b, which is the optical path length difference between the two rays, is equal then to a times theta, and so that's going to be approximately, or it's approximately a theta, which is then equal to a y over L. Okay? And so this is actually our difference, R2 minus R1. And then that allows me to say that, okay, that when I have that the path difference, or the OPL, when the OPL is equal to an integer number of wavelengths, then all the peaks and troughs are going to line up, and where m's an integer. And so I'm going to have constructive interference. And so that allows me to say that y max, so the position on the screen where I'm going to see a bright fringe, which is constructive interference, is going to be given by L over A, and then m times lambda. And then the angle that corresponds to, the angle where I'm going to get a bright fringe, is then m lambda over A. So these are very important equations. These are the statements. I'm going to put this actually in a double box, because these are the results for the Young double slit experiment.